Welcome to Innovate and React. I'm Kevin Hares, and in today's episode we will talk about how we can turn methane into value chemicals via photocatalysis. I'm here with Dr. Andrés Constantino, who is currently a postdoc at the Institute of Organic Chemistry in RWTH Aachen. Welcome, Andrés. How are you?
Thank you so much, Kevin, for your kind introduction. Also, thank you for inviting me here today.
Yeah, I'm happy to have you.
It's a big pleasure, and always it's a big pleasure to discuss about cool chemistry. So thank you so much.
Yeah, I'm also excited about learning more about this photocatalysis. So maybe let's start with why do we want to turn methane and these low functionalized molecules into value chemicals, and why is that not done already?
Well, in fact, these light hydrocarbons, methane, ethane, propane, and so on, we need to point that those are naturally occurring. They are present in natural gas. So we don't need to synthesize them, and we could just use them directly to the synthesis of complex structures in organic chemistry. Mm-hmm. However, currently, the main use of these hydrocarbons is most of the time is just they are burned to produce energy.
Yeah. I guess that's where everyone knows the methane from, like the natural gas and the gas stove at home. Yeah.
Yes. The main big application, and it's a pity because during its extraction we are consuming energy, we are producing greenhouse gases, and then when we have this enriched carbon source, we are burning them again to produce energy and release greenhouse gases again. Yeah. So it's a little bit it's a cycle, but those compounds are not transformed in something really, let's say, useful.
Yeah, exactly. And I think also in terms of the transformation of the chemical industry, where we want to go away from these fossil fuels in general, but we need to get the carbon from somewhere. And in my opinion, we should, as much as possible, go away from fossil fuels in like the energy sector. But for chemicals, well, we kind of still need the carbon source, and then it's better to use all the carbon sources we have. So methane would be a great addition.
Yes, I agree completely. Organic chemistry, luckily or sadly, depends on carbons, so we need to get the carbon from somewhere. But apart from fossil fuels, we could also obtain methane from what is called biomethane from wastewater or diverse amount of trash, and just with the proper anaerobic digestion, we could get as well those hydrocarbons.
Yeah, definitely.
The green alternative or the sustainable alternative exists, but it's still very underdeveloped.
Yeah. And also those biogas is used as a fuel usually, and then we can use it to make much higher value chemicals. And well, there are already some plants who use these ethane and stuff for making chemicals, but what's the problem with those? Like, I think there are natural gas crackers that should replace steam crackers with mineral oil. But what's the problem there?
Yes, in those processes, the energy consumption is huge. It's not just an extra step, but it's an extra time consumption, extra energy consumption, extra waste generation, and at the end is extra money, which the company needs to waste in these transformations. Yeah. So it could be ideal if you can just get your methane, remove the hydrogen, and attach it to an organic molecule rather than just inserting an iodine or a chlorine or the oxidation to methanol, and from there starting diverse routes.
Yeah. So directly use it, and then, for example, also the workup steps in between, they usually involve all kinds of solvents, and the energy consumption is high, and then you could save all this if you use the methane directly in your reaction in the synthesis steps. But as we said before, the alkanes are not really reactive. Like, that's what they're known for. They can burn.
Yes.
But to start this, they also need a lot of energy. But there are also some other processes which use alkanes for the functionalization. What are options there?
I think the most common ones are the oxidation to corresponding alcohols like methane to methanol or methane to formic acid. I think that those can be the most common ones. Also the chlorination, the direct chlorination of methane with chlorine gas under very harsh conditions. So at the end you have chloromethane and potentially some over-halogenation products.
Yeah.
But yes, these procedures usually require very harsh conditions and sometimes not very safe chemicals.
No.
In the oxidation, most of the times you need peroxides. In the halogenation, you need a chlorine gas, which is not easy to handle. And also, these reaction conditions are not compatible with the presence of any other organic molecule.
So you make the methane more reactive, but then you need additional steps to use this activated carbon chain then to attach it to whatever you're trying to synthesize.
Yes. It's, like I said before, every extra step you introduce to make the methane more reactive, yes, it will be, at the end, will be easier, or you can just use more traditional or straightforward chemistry, but it's again extra time, extra energy, extra waste generation.
Yeah, of course. And then you looked at allylation chemistry. So why did you choose that kind of chemistry?
This reaction we developed in the group where I did a PhD, in the group of Martín Fallanas at CICUS in Spain. And in our group, we have an important background on allylation chemistry. So for us was quite evident that in the literature there was a big gap about the allylation or the direct allylation of gaseous alkanes. Now, in the literature you can find plenty of Giese additions, which generate the radical of your hydrocarbon, and it's directly added over a Michael acceptor. And this reaction works really, really nice.
What is that usually used for, this Giese addition?
Well, a Giese addition is the same as a Michael addition, but with radical nucleophiles, let's say.
Oh, okay.
Yes. But if we compare the products of allylation and in the Giese, we have a double bond, which is highly activated with electron withdrawing groups such as esters or cyano groups. So the radical addition of the hydrocarbon, which is a very nucleophilic radical, adds very easily to a double bond, and then this double bond is deleted. So at the end, you insert your alkyl fragment, which is so cool, but the olefin is gone.
And that you want for further steps, because the double bond usually can be functionalized easier. Yeah,
that's the main point from the synthetic point of view. And in the allylation, we have the olefin alpha to a leaving group. So we have the addition of our nucleophilic radical, then the olefin migrates and the leaving group is gone. But we still have the olefin, and that's the thing. The olefin you can still doing a Hecker reaction, oxidation, oxidative cleavage, epoxidation, halogenation. So we still have this very versatile functional group to make further organic transformations.
Yeah, you also have shown that in the paper, and we come back to that later, how you further use this compound then. Quick break. 2 things I want to tell you. First of all, a big thank you for tuning in. This really means a lot to me. And secondly, if you like chemistry and learn something from this show, please subscribe on whatever app you're listening. It will help me to get new guests on to continue. Thank you so much. Back to the episode. But first, you also used photocatalysis to mediate the reaction.
Yes.
Why not other catalysts like a transition metal catalyst that I'm very familiar with, or other organic catalysts?
Yes. Transition metal catalysis would be amazing, because you can just put the organometallic catalyst in your reactor, then you close the system, and the organometallic catalyst is doing the chemistry. And the scalability problems of photochemistry are not present, because you don't need to irradiate, so everything will be more straightforward. But what we have with gaseous hydrocarbons is that they don't have any kind of linkage to the organometallic complex. They do have a lone electron pair, as maybe directing group has, which can anchor the organometallic complex to direct the CH activation, or any double bond which can also coordinate the metallic core and assist the introduction or the activation of DH. And in this case, the light hydrocarbons doesn't have none of these anchoring sites.
Yeah, they cannot really coordinate to the metal and then interact with it.
No.
Also, they are very, in case of methane, they are very symmetrical, and it's difficult to attack in the carbon.
Yes, and just at the end, basically carbons and hydrogens.
Yeah. And those bonds are quite strong. But I think also the beauty of photocatalysis is that it's very mild conditions, right? You don't need a lot of heat. You have your light source, and that's performing the reaction. Whereas otherwise you need to heat, usually to quite high temperatures.
Yes, but also the light, it depends which wavelength are you using. That could be also a drawback. If you're using red light, okay, that's very friendly, it's compatible even with live cells. But when you go to ultraviolet light, then you have a lot of issues with compatibility with certain functional groups, which might be active also in UV light. So that in that aspect is a little bit tricky.
Okay, so maybe not for the very late stage functionalization when you have a lot of stuff there.
For later stage functionalization, there's actually a lot of protocols using UV light. I mean, it can be an issue with certain functional groups, but usually it works quite well.
And now for your reaction, how did you use the photocatalyst, and how did you overcome this problem of the really almost inert CH bond in those alkanes?
Yes, in the last years became very popular these hydrogen atom abstraction protocols, and what we are using is photocatalyst, which under light irradiation generates a highly active chlorine radical. And this chlorine radical has the power to abstract the hydrogen from the gaseous alkane. So you form HCl and the alkyl radical.
Oh, okay. Interesting. Then maybe for the listeners, quickly introduce your catalyst system. I think then it's also easier to understand where the chlorine comes from.
Yes, our catalytic system is iron trichloride. aqua in combination with Collidine, and that is the catalytic system. So we irradiate, and then the iron is excited it's excited, and then the homolytic cleavage between the iron and the chlorine takes place, and you generate an iron 2, and then the chlorine radical.
And then the chlorine radical reacts with the alkene to abstract the proton. What happens then after with the proton?
This proton remains in the as HCl form, which is quenched by the Collidine. Which the Collidine has, I don't know if we are going to come back again to this, but it has a dual role. It has a role there as a base, as usually it has, but also as a role of ligand. And that's something very cool we found in this work.
Yeah.
And without Collidine, the reaction is barely working.
Yeah, I was wondering why you did use 2 equivalents of the Collidine. But then, if it accepts the proton later on, then that makes sense. Yeah, cool. You also looked at the mechanism, and the Collidine is the proton acceptor in the end, but how does it also interact with the catalyst in the reaction?
Yes. We found, I don't know if by serendipity, but the truth is that we explore a lot of conditions. In fact, we start the optimization reaction just first of all evaluating very carefully all the reported protocols for activating gaseous alkanes. None of them work. And after a lot of screening of bases, ligands, additives, we found that the specific addition of 3 equivalents of Collidine was the optimal and was crucial for the reaction working, as it is working. So we were wondering why Collidine.
Yeah.
What is doing the Collidine which cannot do other pyridinic base like pyridine? Because pyridine is working the reaction, but no as nicer as Collidine. And we were very, very lucky. Our colleague Paul could obtain an X-ray quality crystal. And we found that the Collidine is establishing a dense network of hydrogen bonding between, actually it's Collidine hydrochloride, establishing a dense network of hydrogen bonding between these units and a core of iron tetrachloride anion. So you have a core of iron tetrachloride anion interacting with 3 collidinium cations by hydrogen bonding, and then the 2 remaining chlorine anions are just in the lattice of the X-ray structure. And this supramolecular ensemble helps to stabilize the complex. We are increasing the photostability, but also we are shutting down side reactivity.
What side reactions can occur there?
When you generate a highly active radical, like these alkyl radicals, it's known that those radicals can attack to metal halogen bond, which is called radical ligand transfer. So what we were observing a lot of the times when Collidine was not used is the formation of big amounts of the corresponding alkane chloride.
So basically the radical is stealing the chlorine from the iron chloride?
Yes, and that was leading to low conversions, very low yields, because the active catalyst was engaging inside reactivities. But when we have this supramolecular complex, we have the central core of the iron tetrachloride, which is tetrahedral, and only one of the chlorines is free. Let's say it's free. It's in an axial position and it's free. It's ready to make the homolytic cleavage after the excitation and generate the chlorine radical. The other 3 are interacting with the collidinium cations through the hydrogen bonding. So those chlorines are not available for any kind of reactivity, not for the LMCT, and not for this radical ligand transfer. So, and when we don't have the Collidine, the active species, which is the iron tetrachloride, just itself in the media, has the 4 chlorines exposed to the reaction media, so the probability of some alkyl radical doing the attacking this chlorine iron bond is much more higher than in our case.
Okay. Yeah, that's interesting how basically the structure of the whole complex then makes or protects somehow this catalyst, because the active catalyst itself is just then the iron chloride. So it would also work with very low conversions with just iron chloride, but it would not work with just the Collidine.
Yes. And that's just the active species in this chemistry, in this photochemistry of iron trichloride, actually is the iron tetrachloride anion. In solution, 2 molecules of iron trichloride form an iron tetrachloride anion and an iron dichloride cation. And what we have in our system is radical acceptor, which is the allyl chloride, which is not as activated as the Giese acceptors. So if we go to the Giese chemistry, we can see that all the chemistry with iron trichloride is just iron trichloride, radical acceptor, and gaseous alkane. They don't need any kind of base. Because the radical acceptor, the Giese acceptor, is extremely activated. So once you form the methane radical, it will directly act on the radical acceptor.
And then also the proton doesn't need to go elsewhere. Then it
and
goes
then
to
the proton is also quenched by the resulting product. Yes. In our system, the allyl chlorides are not as much activated, so we need to compensate this low reactivity of our radical acceptors with the high reactivity of the iron chlorine bonds toward the radical ligand transfer. So it was a balance.
Yeah. What I also saw when I looked at the different yields you got, because you also looked at other alkanes, ethane, propane, and the yield seemed to increase with the chain length. And in the introduction, you also mentioned that there are already protocols for the liquid alkanes. So why is it that the shorter the chain length, the lower the reactivity?
Yes, when we talk about the strength of carbon sp3H bonds, the smaller the molecule, more difficult is to abstract this hydrogen. And this is because first of all, or mainly the radical stability. In the methane, we are going to form a carbon center radical, which only has 3 hydrogens to stabilize the radical. So it's not the most stable radical in the universe. But when we have isobutane, for instance, we still have an alkylic chain which can stabilize the radical, or cyclohexane. This radical is a secondary radical, so the abstraction of this hydrogen is much easier and can be performed in milder conditions. That's also why we need to go for higher pressures of methane. Like I think we're using a 50 bar. For ethane, which is easier to activate, we use 8. And then propane and isobutane is 1 bar. That's why, because we need higher concentration of the alkane to promote efficiently the CH activation.
Yeah, because then the radical is not as easy to form. And so basically this very basic organic chem lecture stuff with the stabilization of the radicals. Interesting. Yeah, and then talking about the scope of the reaction, you used all kinds of different allylic chlorides, which is great to have this versatility. In the beginning, we talked about that other protocols which use harsh chemicals, they have a bit of a problem with other functional groups, and you could show quite a big scope. What were the limits?
Of course, the best ones are the electrodeficient allyl chlorides, because the alkyl radical is a nucleophilic radical. So if we have a very electron poor radical trap, the recombination will be very fast. That's the situation we have with the Giese addition. So we observe that when we have electron withdrawing groups, the reaction is really, really fast. In fact, we are getting almost quantitative yields. But while in the other cases, the reaction still proceeds, but the yields decreases a little bit to 70s, 60% of yields, which are still good, talking within this context of gaseous alkanes. But yes, I think that could be a little bit, let's say, the limitations of the method.
Would be, very electron-rich allyl chlorides.
Yes, that would be for sure a problem. I mean, we didn't evaluate, I guess, any very, very electron-rich one.
Yeah, but still, it's it doesn't have to be super electron poor to work, which is quite good.
No, just in fact, I think that we use aryl rings substituted with a methoxy group, which is a strong electron donating substituent, and the reaction proceeds around 50s, but still it works.
Yeah. So this is again when the acceptor in this case is more reactive. You have less side reactions probably, because then the radical really readily reacts with this acceptor and not other places.
Yes.
And then in case of application, or you already showed some nice application of this in a larger synthesis route.
Yes, we demonstrated the synthesis of the dimestrol, which is a non-steroidal estrogen used in hormonal therapies. And to the best of our knowledge, as we also say this on the work, this is the first synthesis of a bioactive compound using methane as a starting material. So we are demonstrating that we can use these small little hydrocarbons to build some bigger and complex molecules, and we have around 20% of the overall yield, which is actually great if we are talking about methane, because sometimes you are doing chemistry in your lab, very traditional organic chemistry, and after 3 steps you are also in the 20% of yield, and you don't do that.
Yeah, I think in that reaction, the methane is so cheap that if you lose some of that, it doesn't really matter, right? You need to convert the other reagent. That's more important, right? Did you also look into the conversion of the other side of the reaction?
Usually, the allylic chloride, in most of the cases, we still recover some of them. So, and we can isolate back from the column. So ideally we can get it and rerun again the reaction. So we are not just destroying the allylic chloride, which is great from the atom economy point of view.
And you can just do the cycle again, and then it's not really a problem. And also, in terms of the end product, which is quite a complicated molecule, it's then very great that you can use such a simple molecule to start with.
Yeah, and also from the point of methane, of course we are using 50 bars of methane, which is a lot, and we are only, in this example, we are only using 0.1 millimole, which I don't have the numbers in my head, but maybe that is like 1% of the 50 bars or even lower. But from a bigger scale point of view, the methane is still on the atmosphere of the reactor, so it could be easily just redirected and recovered to again to the methane reactor.
Yeah.
And could be and actually you are not losing methane.
Yeah, exactly. I mean, in the industry, it's oftentimes you don't have full conversion anyway because you want the highest selectivity as possible, so you create less waste, and you just methane is very easy to cycle around. You can just keep it in the reactor. I assume if you would scale up your reaction, you would need some kind of flow reactor to have the efficient light distribution, right? Or how would you scale up this reaction?
We scale up the reaction for ethane and for propane. We scale up from 0.2 millimole to 3 millimole, which is approx from 8 milliliters reaction to, I think it was 30 something at the end, or yes. And we just use a bigger reactor, and instead of one lamp irradiating, 2 lamps. And also a larger reaction time. We went from 16 hours to, I guess, 32 hours.
No, okay.
The yield decreased a little bit.
Yeah.
But
okay. So the larger scale also improves the reaction in that sense. I mean, gets slower but more yield. Interesting. But then, yeah, if you would scale it up even bigger, you said that with larger reactors, it's sometimes a problem for the light to really go into the reaction mixture.
Yes.
How
in that
could you solve
sense,
that?
yes. Ideally, yes, a flow reactor would be ideal for this application. I'm not 100% sure, but I guess somebody else in my previous group was working on that. And also, there's a lot of research in this scale up of photochemistry reactions.
Yeah.
And there's some, I don't know if they are already used, but there are some kind of light balls which can be introduced inside of the big reactors. So the radiation takes place from the interior of the reaction. And these luminescent balls are also spinning inside, so you have direct irradiation inside. You don't have this problem of having lamps outside and going through the solvent and through the reaction. But yes, scalability of photochemical reactions is a big research field.
Yeah. So that would be definitely one way to improve, but this is not really on the reaction optimization side. It's more on the engineering side on how to get light into the sample.
Yes.
What other improvements do you think will come with this reaction?
We believe that our finding with this photocatalyst, this supramolecular photocatalyst, in which we can in some way attenuate this ligand to metal charge transfer reactivity, but also suppress the side reactivity of the radical ligand transfer. We believe that this may open new doors to use even less activated radical acceptors. We believe that, because until the date, most of the radical acceptors used were highly activated. Also because most of the groups were doing an excellent research on just developing new catalytic system to demonstrate, okay, I have this catalytic system, and this catalytic system is capable to activate the hydrogen bonds from the hydrocarbons. And most of the research groups were focused on that direction. And to be honest, when you want to prove that your new photocatalyst is working, you're going to choose the most reactive substrate because it's the most straightforward to demonstrate. Okay,
But the challenge then is really to use those who would not really react. Like, what would be an example that would be the dream reaction in this case that you could use?
Oh. The dream reaction
Yeah.
where I could use gases alkanes.
Yeah.
That's a difficult question. I don't know. Maybe a radical addition over non-activated olefin. I think that will be one of the hardest one. Without, of course, the assistance of any second method that may trap the radical and then insert the alkyl fragment in the olefin. Just the direct radical addition of the radical.
Yeah, that sounds very challenging. Okay, and what I also thought when I was looking in this direction, currently I'm dealing a lot with power to X processes, and there one of the ways to go is using CO2 from direct air capture and then converting it to methane, and then you could use that methane also in your reaction and basically use CO2 as the starting material in your synthesis route. Well, very many steps, but still it's an interesting concept.
Yes, it's a very interesting concept as well, and actually there's a lot of research groups doing huge efforts on using CO2 as well, because it's also a greenhouse gas. And that could be another alternative. You are still adding intermediate steps, in this case to reach methane, with, I don't know, honestly, I don't know if would be the best choice to transform CO2 in something very inert, such as methane. But, well, nowadays with the toolbox of gaseous alkanes we have to activate them, could be a useful transformation for sure.
Yeah, but you're right. Probably it's easier to use something like methanol or other more activated C1 structures and then use those for the further chemistry than the methane. It's just a theory thought. Then to close this discussion, I always ask in the end the question, what's your favorite discovery in chemistry?
We have a lot of them, and that's a difficult question because no matter which one I will choose, somebody will complain about it. Probably the structural elucidation of ferrocene.
Okay.
Ferrocene, which was an important inflection point on the organometallic chemistry. And it opened a lot of doors to synthesize and to design novel organometallic complexes, organometallic reagents. I think that will be one of my favorites.
Yeah, that's very impactful for catalysis, definitely. Okay, thank you very much for this discussion and sharing your research.
Thank you very much, Kevin. Thank you so much for hosting me today.
Yeah, it was a pleasure. Thank you very much for listening. If you like chemistry and don't want to miss a future episode, don't forget to hit the follow button. This already helps the show to grow. You can now also support the show on Buy Me a Coffee to help me keeping it running. The link is in the show notes. You can find the link in the show notes. If you would like to be part of a future episode and talk about your research, send me an email to contact@innovateandreact.com. And until next time, keep innovating and stay curious.